Hello everyone. I'm going to talk about representing music on computers, specifically in Haskell. And I'm going to be talking about my own personal discovery of an interesting era of music and the interesting sort of, tuning systems that we used. And I will be showing a way of representing notated musical notes, which is slightly more general than what you might be used to on a computer. So slightly more general than the MIDI having an integer from 1 to 12. And this comes in useful when trying to play music written in early 17th century Italy. And I hope that, just because it's a nice generalization, you all might like to sort of write your notes this way on a computer. So this is sort of my motivation. The two images at the top they're the same instrument, made in 1606 in Italy, and it's known that the composer Luzzaschi played a keyboard like this, was in fact very skilled at it, could improvise on it, and other people were caught in one of the Italian cities. And this picture here, this is a modern copy of another keyboard from that period in Italy, which has 19 notes per octave. Sorry, if you look carefully here, this one has 31 notes per octave. This one has 19 notes per octave, and you might think, what's going on here? They just add notes at random. But it turns out it's not completely random. They had a very clear idea of what it meant to have multiple notes per octave. And this is just a little excerpt of a piece of music I'll be showing you later, written by Guillaume de Costerly, a French composer in the 1580s or so, written specifically for a keyboard that looked like this, with 19 notes per octave. And as you can see, there are lots of weird accidentals, a lot more than you might expect from a piece written in the 1580s. So what I'm going to propose is that you think of the possible space of musical notes. This is notated notes as you would write them down in the Western musical tradition, not as just numbers from 1 to 12, what you might call pitch glasses, but as points in a lattice, an infinite two-dimensional lattice. And this is probably, well, it might be familiar to you because it has been used in music theory quite a lot, this idea. And the musical intervals, basically every difference between a note and this lattice is an interval, and if you look at all these intervals together, they form what's essentially a two-dimensional vector space, though there's no notion of length. So strictly speaking, you should call it a free abelian group, but everything you do to it is just a two-dimensional vector algebra. This is a picture of a lattice of notes. Just imagine this stretching off to infinity in every direction. I could have drawn it on a square, but I've offset it slightly just to make it clear that the sort of distances are arbitrary. So you have to imagine that these are all the possible notes you could write down, and you're not assuming that any note is necessarily equivalent to any other note. So you might think, why are we interested in there being a D double flat? Isn't that the same as a C? Well, no, we don't know it's the same as a C, at least not if we're in Italy in the early 17th century. And this goes on to D triple flat, D quadruple flat, etc. to infinity.
Sorry, where's 0 on one of the generators?
Yeah. The generators are any two independent intervals. So, for example, these two. And 0 is, well, you just take one of the notes to be your origin.
Right, it's more like a torso or something. That's fine.
Yes. So, for example, this is a major second and this is a minor second. They're independent in the sense that one isn't a multiple of the other, and that's good enough to use those two as the generators for the whole lattice. But you can pick any two. So this is the fifth and the octave, and this is an augmented unison and a diminished second, which is a bit weird, but I'm going to come back to this in a moment because this is in some ways a nice preferred pair of generators. In principle, it doesn't matter at all, but for implementation purposes, it's nice to think of things like this. And now we come to tuning systems. These two types of tuning systems don't cover every possible tuning system that everyone has ever come up with. There's this weird zoo of tuning systems that exist out there in the real world. I sometimes struggle to understand how to apply some of the stranger ones to real music that I see in front of me. But certainly these two work very simply in the context of the representation that I've just mentioned. Basically, you pick two ratios between frequencies, and then you just assign those to the two generators, and then that gives you the frequency ratio at any interval. And then given one note with a fixed frequency, that gives you the frequency of every note, and then you're done. And there are two types. One is where in the map from notes to frequencies, you maintain the two-dimensional structure, and that's the sort of class of tuning systems called syntonic temperaments. And there's the other type, which is called equal temperaments, which is the same except you're projecting away one of the dimensions. So these are two so-called syntonic temperaments, which are pretty standard. The first one is the Pythagorean, where you set the octave to be a ratio of 2, and you set the perfect fifth to be a ratio of 1.5, and that gives you everything. And another one, which for some reason musicologists call quarter comma mean tone, but the actual description is much simpler than that. You set the octave to be 2, and you set the major third to be 5/4. And crucially, you only get two choices. There's no additional freedom. And then here are some equal temperaments. The one which we're all familiar with is dividing the octave into 12 equal steps. It turns out that this is equivalent to projecting out the diminished second. So if we just go back to the lattice, if you imagine every D2 vector, so every vector which points downwards like that distance, gets collapsed down to the bottom, then all the notes which land on top of each other become equivalent. So then, as you're probably familiar with, a D is the same as an E double flat, and C sharp is the same as D flat. B natural same as C flat. Anyway, but you could project any interval out, and the way you get 19 notes per octave. So sorry, about the 12 equal temperaments. When you do that, you end up with 12 notes per octave inescapably. But you could pick another interval to project out, and if you doubly diminish your second and project that out, you get 19 notes per octave. If you project out the quadruply diminished third, you get 31 notes per octave.
So what does double diminished second mean?
It means...
Is that something in your lattice? Is that visible in your lattice?
Yes, the double diminished second is the difference between... what would it be? It's the difference between B sharp and D double flat. But you could find another way of writing other generators and think of it in terms of that. But this is, at least for that particular tuning system, the simplest description. And now I'm just going to come to, before I give a demo, just some details of my implementation. It follows the sort of standard way of representing music on a computer, which is that each note is a pitch and a duration. But I haven't gone more elaborate than that, and that's all you get. A phrase is a list of notes, and because I'm focusing on polyphonic music, even the keyboard music of this era is polyphonic, for multiple notes at once, I just stick phrases on top of each other, and to get from one phrase to the next, you connect it. You can connect the beginning of each phrase at any point to a previous phrase, so you get what's called a phrase tree. And then in turn, all the calculations internally are done by converting every interval to the basis A1, D2. So if you remember the A1 takes you up a sharp or down a flat. And the D2 is the interval which changes the letter of the note without changing how it would sound hypothetically if you were using 12 equal information. So you could say that diminished second changes the number of the note, or the degree of the scale. And then the mathematical interest behind it comes down to two-dimensional linear algebra. Because if you want to specify two arbitrary intervals, normally one would be the octave maps to 2, a frequency ratio of 2, and then you have another one for each. But it could be any two. If you specify that, you have to invert a 2x2 matrix to get the correct map from any note to frequencies. Okay, now I'm going to do a quick demo. So this is the Haskell prompt. So as you can see, there are defined just large enough for people to see. Yeah. I've predefined the sort of normal notes that you might be familiar with, and using the operations in the this is the vector space type class in Haskell. You can add intervals to notes. This is a standard operation in any sort of music theory program, but I'll rapidly show that normal music theory programs will break as soon as you try to go too far off the edge of the lattice. So for example, to get from a C to a C sharp, you add an augmented unison. Let's say you wanted to add 3 perfect fifths together, you get a major 13th. So far so good. What if you wanted to add 5 semitones together? Well, you get a quintuply augmented unison. Now you might think this is not useful at all, and maybe that's true. You don't want to play a quintuply augmented unison, but if your set of intervals is closed under all the sensible operations, and if you know that that's true in the sort of back end of the program, then, well, you can reason about it better. And implementing some of these tuning systems is much simpler, because you don't have to fill your code with awkward special cases. For example, if we subtract, add that interval to the C, we get computer passion. Subtract a load of font. This is 2 double sharps and a normal sharp, in case you're wondering. So, C quintuple sharp. Okay. And just to show that you can perform calculations that might be useful in music theory, this sort of fun fact about Pythagorean tuning, or about the music scale in general, is that if you add 7 octaves and subtract 5 perfect fifths, you get a diminished second. Well, you get what people might normally call the Pythagorean comma. So what you really get is the interval such that if you tuned it in Pythagorean tuning, the frequency ratio would be the Pythagorean comma. But we haven't assumed yet that it maps to anything. We just know that we get the diminished second. Okay. The generic way of writing a tuning system here is this thing I've called arbitrary symptomic, which means take 2 arbitrary intervals, give them frequency ratios, and then specify an origin for the lattice of notes. So here, we're going to go with Pythagorean, set the octave to 2, the perfect fifth to 3 over 2, and then the origin will be A at 440 Hz. And as you expect, if you choose this as a tune interval using the tuning system we've just defined, we get 3 over 2 for the perfect fifth. we get some number which isn't quite right for the major third, which is 81 over 64, as we've just verified. And for the D2, we get the Pythagorean common. And I'm just going to demo playing some notes. We made a phrase of C major scale, and if we want to play this, we have to map the tuning system to it. By creating a function that maps the specified tuning transformation over all the notes in the piece of music we just made. Okay, and now I'm going to demonstrate playing a piece of music, the piece of music that I showed you an excerpt of before, which is the piece by Guillaume de Costerly, where the octave is divided into 19 notes. So that's the score. So I'll just point out, when we get to some strange stuff happening, these are relations that don't exist in normal music and would not sound at all correct if you tried to play in any other tuning system.
for the break, but maybe we can take a question.
Roughly how much of that was notes in a 19-note scale that aren't in the 12-note scale?
Well, it's more that every time that normally you would play the same note with G flat and F sharp,
Yeah.
two different notes isn't the same.
So this is a theoretical question about the model, which is sounds great, but this is clearly discrete music. Does your model extend to what's called glissandi, like slides, where you have a continuous change of pitch? Which seems, it's sort of a continuous value, continuously varying values between C and D, for example.
You'd have to. It doesn't really fit neatly into the sort of map from notes to frequencies. You'd have to put some special directive in the score, like a starting pitch and an ending pitch.
Okay.
Are there any recordings of pieces like this one you just heard?
This particular piece, I found a synthesized version of it on the internet, already done. But as far as I can tell, the only way previously that it can be done is you can do, for example, microtranal output of MIDI, but you have to go through and specify every frequency by hand. And there's no, so this is sort of systematically taking the same note that you see, music that you see on the page, and it works out what the frequencies are.
Recordings by humans on actual instruments.
I don't know. I mean, you could. If there are a few harpsichords surviving with 19 notes per keyboard, so you could play it. I'm not sure I've heard an actual recording of one being played, but.
Have you thought about how you could extend that to other temperaments, like well temperament, things like that?
That's an interesting question. Currently, I'm not considering well-tempered systems. The way they work, or the way I think of them as working, is you know ahead of time you have 12 notes per octave, and then you pick a set of 12 frequencies that's a sort of good compromise. It's not totally arbitrary, because sometimes you tune half of them in quarter from a mean tone and half of them in some other sort of mean tone. So maybe specific temperaments could be systemized well, but yeah.
How long did it take you to enter the music?
Well, it's a Lilley file. And there's, the other part of the talk which I didn't get around to is there's a Lilley parser with this program. So yeah, it's something a program I'm familiar with, so it's not too slow.
I suggest we keep the rest of the questions for the coffee.